And recording is in progress. So, Stefano?
Yes, good morning, everyone, and welcome to this DATAPLAT workshop. I'm Stefano Rizzi from the University of Bologna in Italy. Well, we had sincerely hoped that this year we could physically meet, but well, unfortunately, this was not the case. However, I'm sure the workshop will be quite exciting and will host very interesting discussions, nevertheless. So, first of all, let me mention the team of my co-chairs, Matteo Francia and Enrico Gallinucci from the University of Bologna, and Patrick Marcel from the University of Tours in France. Many thanks to all of them for the support and for organizing the whole thing. Also, I would like to thank Temis and Maya, the workshop chairs of EDBT, for supporting us and above all for timely answering all our questions. Finally, many thanks to the program committee members for the excellent work they've done. Okay, here is the list. I will not reading the whole list, but really thanks to all of them. Well, now let me give the floor to my co-chair Enrico, who will briefly show some stats and the workshop program. That's most important. Thanks, everybody, and enjoy.
Okay, well, thanks, Stefano. So we came up with the idea of this workshop, seeing how the big data revolution has imposed a change into information systems, which have evolved into these complex ecosystems, these complex data platforms, where you have many challenges to address, which are not just about storage and analysis, but it's also about providing more complex functionalities in terms of integration, in terms of orchestration and provenance, which allow you to regain the control over the data, and which requires you to deal with a lot of challenges in terms of metadata collection and activation, in terms of dealing with multiple storage with different data models, different computation engines, and above all, trying to provide these functionalities to users which are maybe not as skilled. They're not very fluent with querying languages and technical skills. So you want to provide them in these functionalities in more automatic ways as possible. So just to give you a couple of stats, we've received overall 9 submissions from around the world, mostly from Europe, but from America and Asia as well, with submissions, with many contributions discussing data platform solutions at a high level. But we also have more vertical papers on data preparation and data migration, data structures, and also automatic machine learning. And of these submissions, we accepted 2 papers, which are long research papers, and 4 short versions. The selection procedure has been done between the end of January and the beginning of February, with reviewers quite, well, again, mostly from Europe, but we have representatives from most continents as well. You can see the average score that were given by the reviewers, and we managed to give between 2 and 4 reviews for each paper. So the program, we're going to start with the keynote session, and after that there's a research session with actually just 1 paper before the coffee break, and then we're going to resume after with another session with the remaining long and short papers, and then we're going to meet again at the end for a quick farewell. And before we begin, let me remind you that the best papers of this workshop are going to be invited to special issue which is titled Advances in Data Platform Design, Management, and Optimization, which is hosted by the Future Generation Computer Systems Journal, which is quite an important one. Invitations will be based not just on the originality of the paper and on the reviews, but also on the quality of the presentation. So good luck to all the presenters. Invitations will be sent next week, and be sure that they do not ensure publication. Okay. But I would also like to remind everyone that this special issue is actually open to everyone. So even though you do not receive an invitation, you can still send your contributions. The submissions are actually open right now, and there's time until the 15th of July to submit papers. And the reviewing is on a continuous basis. So the reviewing process is going to start as soon as the submission is sent. Well, that's it. So we're ready to start. Let me stop the screen sharing. And we're going to start with the keynote session. So it's a great pleasure for me to introduce Alberto Abello, which is a professor at OPC, which is the Universitat Politècnica de Catalunya in Barcelona. Well, he's got plenty of experience in the fields of business intelligence, data analysis. Lately, he's been focusing a lot on the management of big data and metadata. Today he's going to talk to us about big database management systems. So, Alberto, please, you can share the screen and start with your keynote.
Let me see. Well, first of all, thanks a lot for the introduction, and especially for the invitation. It's a pleasure to me to be here. And see, you see the screen, I guess.
Yeah.
Yeah, we do.
Wait a second. Here. So what I'm going to present today is not only my work, but the research that has been done in the group during the last years, and especially some slides also come from Sergi and Oscar. And what I will try to do is to provide you some framework maybe for further discussion during the workshop. Kind of, this is the idea that you can relate the contributions of the different papers that will be presented to what I will explain now. So first, I will try to introduce the problems that most probably you are already aware of, and then some data science or data engineering specific tasks, just to frame what we are talking about, and then the maybe well-known solutions that are right now in the community, in the both, I mean, industry and academia. And then I will focus more in our approach to these problems and our solutions to these problems. Okay, so how we relate these to a database management system, or to a new generation or future generation of database management system, and which is the relevance of metadata in all this. Okay, so about the problem definition, the idea or the main purpose is to apply machine learning in the end, or data analytics in the end. But around this data analytics, I mean, if you see here, so here there is a lot of buzz, I mean, a lot of relevance about the machine learning and so on. But in the end, it's a very small module, a very small task in the middle of, or surrounded by many other tasks more related to the management of data and the software around all these that allows in the end to enact these models that we develop in the analytical tasks. So the focus of the talk is just removing this, and then we focus on all the other tasks that surround this machine learning, which is in the end, in most of the cases, most of the work, so the big part. So about this data management, just to some basic ideas. So we have some data that can come in the form of CSV files or JSON files or whatever, and we need to ingest this and maybe just upload this into the cloud. And then we have here some physical structures that can be B-trees, LSM trees, hash maps, or whatever data structure, physical data structure we want to store all this data. And then we have some views that can be relations, can be data frames, can be matrices, can be whatever. And but in the end, basically they are instances with different features. And then we provide some mechanisms that allows to the users, to the analysts, to retrieve this data. So we need some processing engine that maps somehow this physical structure to the abstractions we have. Okay, this is the overall idea. So related to data management, we refer to the functionalities of a DBMS is providing. So which are these? I mean, first of all, data ingestion. So if we talk in terms of Oracle, for example, the tool that it provides is SQL Loader, just to ingest the data or upload the data into the server. Then about the storage, we have different structures, can be hash, can be trees, can be heap files, whatever. About modeling is how we arrange this data in this structure. There is well-known normalization theory. Also partitioning is possible, etc., etc. Then about the processing, we have PL/SQL in relational DBMSs, and then for querying, I mean, we have SQL. We can use relational algebra, etc., etc. Okay, so in big data settings, we have exactly the same problems, but in this case, what we are assuming is that we have no SQL tools. Okay, we move away from the relational model, because this is typically happening in a distributed system, and then we need, I mean, highly scalable systems, and we implement more ad hoc architectural solutions, and this is the problem we need to tackle in this case. Okay, and because of volume here. Volume, velocity, variety, variability. Okay, we question the main principles of the DBMS architectures, because, as I said, we need to scale out. Maybe we don't require persistency, and the structure of the data is not well known a priori, etc. Okay, so the solution to these problems is that we re-implement the functionalities of the DBMS, but we just mentioned integration, ingestion, storage, modeling, processing, querying, etc., etc. And then we use, I mean, to cope with these new challenges. Let's say we use some specific technologies. Let's say like distributed trees or dynamic hash, and in-memory processing, some columnar processing as well, with some kind of encoding, and also try to benefit from sequential reads. I mean, parallelizing, etc., etc. Okay, so in the end, what we end up is, instead of having a monolithic DBMS, we end up with a multi-project, let's say, approach, where the DBMS that we see as a whole in a relational traditional system actually is implemented, or these functionalities we mentioned are implemented through independent components, are heterogeneous components. So they are not one single monolithic system, but in the end is composed by different pieces. Like, for example, in the case of Hadoop, we have HDFS, HBase, Catalog, Scoop, Spark, SparkSQL, etc., etc. Okay, so if we are not careful with this, I mean, the problem is that we have a lot of tools. I mean, today there are hundreds of NoSQL tools, if you want to call them like that, or tools for big data management and analytics and so on, that in the end we need to connect, and we need to make them to interact and exchange data and metadata, etc., etc. So we need some plan, let's say. So we need some blueprints to connect all these tools and make them give the view of a unique, a single DBMS, let's say, in the end. Okay, so here we have some figure of what was happening in LinkedIn, for example, some years ago, which was kind of a spaghetti architecture, let's say, in the sense that there was not clear blueprint or plan for the connection of the different components. So they ended up just growing in a, let's say, irrational way, or I don't know how to say. So you end up having problems in the long term, in the maintenance and sustainability of this system. Okay, so this is the problem we are trying to avoid. Okay, or this is the situation we are trying to avoid. Okay, and that's why we need this architecture, that this is the focus of the work. Okay, so before going to the solution, let's try to understand which are the main tasks, or which is the purpose of this system we are trying to build. So given that in the middle of the core of all these projects are the machine learning and these models that we are trying to build, in the end there are some specificities because of these big data challenges that I already mentioned. You know, there are some specificities in the tasks that from the point of view of the data management. Okay, so let's look first at these specificities. So I mean, you can distinguish here. I mean, we have some tasks that are automatic, some others that are more with some assistance or feedback from the user, and some that are completely manual. Okay, so we have the three degrees of automation, and let's say in the task that you can identify, and then we have different artifacts and different data stores, etc. Okay, so one of the characteristics in the big data environments is that the sources are kind of dynamic. It's not like in a data warehousing environment where the sources are mostly the internal sources of the company, the OLTP systems or the transactional systems of the company. But here we have other external sources. So the first thing we need to do is to register, let's say, these sources in our kind of virtual DBMS. Okay, so we need to extract some metadata, and with this metadata we create some wrappers that allow in the end to extract the data later. Okay, so together with this wrapper we can also generate some schema that then we integrate somehow and generate a global schema, and together with this global schema we need to generate some mappings that express the correspondences between the data source and our global schema that we just create. Okay, so this is the first thing we need to do. Once the different sources have been registered in our system, then we can start exploring this data and querying this data, so we can create these queries and send them to the system that should be able automatically to process them. And then if we think that this basic query of the user is not enough, we could extend this data intensive flow. I mean, here we have our data intensive flow, okay, that is generated on resolving this query. Then we can extend it alternatively here, this flow. If not, then we go back and simply execute the flow over our data sources. Then we get some query results. Then we would interpret these results, and then based on this interpretation, we would go back to query the data again and again and again. So it's a kind of iterative process of exploration of the data, and then eventually, when we are satisfied with what we have, then we should just deploy our data flows into production, and then we get the final analysis or the results this analysis. Okay, so let's focus now on how to extend if we are not completely satisfied with our initial data flow, how we can extend it based on some rules. So in this case, we can find that some of the data is not of the required quality. So then we detect some violation of these rules or integrity constraints. So then we repair this data. So it means that we need to modify our flows to maintain this repairing of the data, and then in the end we process this, and then we would continue with the new data flow. I mean, updated data flow after this cleaning or fixing of the errors. Okay. Then if we move now to the deployment, then here we would have in the end different data flows for multiple sources. So we need to consolidate them, and here we would end up with multi-flows. I mean, different queries, let's say, that benefit from partial executions one of the other, and then of course this should be optimized for more efficient execution. And then when this is optimized, then we should just decide on which physical engine, I mean, they are going to be executed. It could be Spark, or it could be Flink, or it could be whatever. Okay, so here we would get some implementation of this flow, and then in the end we would execute the flows, and then finally, as I said before, we get the final analysis. You know, so there are different new challenges or new tasks that appear or are especially relevant in these kind of environments that were not present in the traditional relational monolithic DBMS. Okay, so which are the patterns that we find? So in this case, we move from data warehouses to data lakes. So the idea of the data lake is to load first and model later. So we don't have a schema, predefined schema of the system. Okay, and we just store the raw data, waiting for the analytical tasks to be defined, and then we just decide how to model this. Okay, specific modeling for the specific tasks we have at hand. This is kind of different from data warehousing environments when the KPIs are more clear. Then we have star schemas or dimensional schemas with fact, dimensions, hierarchies, etc., and this is fixed. And then we try to map all our sources to this. Okay, in this case, we go for something more dynamic, let's say, in the sense that we can add sources more easily, and then we can define more on the fly, let's say, which are the schemas of the tools that we are going to use in the analysis, okay, which are the content of this source. So the traditional approach would be model first and load later. So in the sense that we create this schema, which can be multidimensional or not. So for example, we could have 3 different sources with user feedback, product information, or the behavior in the web, or whatever. So we would first define this schema, typically multidimensional, but maybe not. This is not that relevant now. The point is that we map all the sources to this schema, and then we create these data flows. I mean, kind of fixed data flows to load the data from these existing sources to the fixed schema, and then we would plug here some multidimensional tools, some data mining tool, or whatever. The problem with this is, first of all, as I said, these are fixed, permanent transformations. The second problem is that all this schema is fixed as well, is kind of pre-established. So you need to adapt all the sources and everything to this schema. And then in the end, the users need to be aware of these fixed transformations and this fixed schema, so they don't have much flexibility, and they need to learn, let's say, what was done in all this pre-processing that we performed before. Okay, so the alternative to this is load first and model later. So we first have our sources, and then we just create a data repository where we just dump all the data of the sources as we are finding them, and then the different users create different views with different schemas for their different requirements, let's say the different needs, and then they can plug their different tools as well. But the problems in this case is that if you are not careful with this and you allow all the users to simply dump files and files and files without any rules or any control, what you end up having is not a data lake, but a data swamp, in the sense that this is a bit of chaotic, let's say. And then the second problem we have is that these transformations are not trivial, and then all the users end up doing exactly the same transformations and generating very similar flows, etc. Okay, so the idea would be, instead of having a simple data repository, to have a semantic aware data repository. So we need to add here some metadata, some annotations to have some control of what is being dropped in this data lake. So we need some metadata catalog that annotates the contents of all these sources in terms of schema, especially. I mean, which are the features or the attributes they have, which are the data types, etc., etc. And then this metadata should not only have, so once we have all this information of the sources, we should also provide the mappings from these features to whatever the users need. And the idea or the intention is that this somehow helps to automate all these complex flows that then the users require for their work. Okay, so to automate to some extent all these data governance. Okay, so the idea would be we have some requirements from the users, some needs from the users that they would express in some language. So with this, we should be able to extract which are the relevant sources, which is the schema, single or integrated schema for these users, and which are the flows that help to feed, let's say, this schema with the data coming from the sources, and then in the end generate automatically or semi-automatically all the flows that are necessary to satisfy these requirements of the users. Okay, so the idea is that these requirements and then the information related to these sources, to these schemas, to these flows should be processable by machines. Okay, so all these should be driven by the metadata. And just to mention that we don't think that this can be fully automated, but at some point we need the supervision or the involvement of the user to some extent. Okay, so then on the other hand, so this is related to the storage, let's say, but about the processing, which are the patterns we need to consider in this architecture of the big data or the big database management system we are aiming at. So in this case, we have the well-known Lambda architecture. In this case, the idea is that both batch and stream processing coexist in our system. And then, so here in this size would have kind of the batch flow, and here would have more the streaming flow, and both exist, as I said, at the same time. Okay, and this means that we cannot do this independently, okay, because this would create inconsistencies in the data. So if we look at this from another perspective, we have some raw data, then we need to transform this data, and we obtain then some pre-processed data. From this, we prepare this as a training data set for some specific machine learning algorithm, and then we train this and create some statistical model, and then some new data would come. So all this could be done in batch, for example, and then we need to prepare this data that is coming just to use the model we train, and then in the end we just use the data in the stream, let's say, through, I mean, we put this data in the stream through the model we created before. Okay, so the point here, so this is everything, of course, related to data, and the left hand side is batch, the right hand side is in write time or streaming, let's say. But what is important to realize is that this preparation we have here and this preparation we have here must be the same if we don't want to have problems. So if we perform some imputation of values or some normalization of values at the left-hand side, so in the creation of the model, it is crucial that we perform exactly the same imputation, the same normalization or whatever at the right-hand side as well to the streaming data. Otherwise, the model will not work. Okay. So then this moves from the Lambda architecture into the CAP architecture. Okay. So instead of having here kind of the speed layer and here the batch layer, okay, what we have is just one single system where we can have different versions of the job. And then what we do so everything is in the stream actually. So actually we consider everything as a stream, but the difference is that for the batch, we kind of simulate the stream with the batch data. So we just ingest, let's say, the batch data as if it were a stream. So actually we can run both the stream data and the batch data in the same engine. Okay, this is the idea of the CAP architecture. Okay, so we have both patterns. I mean, on the one hand, the data lake, and on the other hand, Lambda or CAP architecture. This is what we are aiming at. Okay, so these are the problems or what we are trying to solve. So let's see which is our proposal in this sense. So this big database management system. So I will give you kind of two views. The first one is the view from the point of view of the components. So we have here different tools that actually play different roles, or the other way around. I mean, we have different roles that then we can instantiate with different tools, and then we see how they are related or how they are connected. Okay. So first of all, some basics on centralized reference architecture for database management systems. So firstly, we have here our query manager with some optimization in the end. So what we get is an access plan that goes through the execution manager. We can have here some scheduler to avoid interferences between different users, and then this goes to a data manager here with some guarantees for recoverability and the management of the memory and the transfer of data between memory and disk in the operating system. Okay, so in the end, if we look at this from some abstraction level, we see that we have some storage, which is this operating system and this data manager. Then here we have some processing in the execution manager and the scheduling, which is part of the transaction processing, etc. And then here we have some mechanisms to manage the query. So we have query processing and storage. Okay. Now we move to distributed DBMSs. So we see that we have basically the query manager as well we had before, but the difference is that here we have a query manager which is global, and here we have a query manager which is local. Okay, so we have one coordinator, but we can have many workers in this distribution environment that we require in our big data or cloud architectures. But in the end, we get an execution plan. I mean, this execution plan would go to the execution manager, but then in this case as well, we have global and local execution manager. Then we have the same scheduler as we had before. It's only global, and then in the end, locally we have different data manager in the different nodes we have in our architecture. Okay, so besides having one coordinator, many workers, etc., what is relevant, especially relevant in this case, is that metadata is more important, let's say, in this case, because we need to fragment, we need to partition all this data, and we need to keep track of where exactly this data is. Okay, so it's not that in a centralized system we don't have metadata. It's just that here we want to highlight that there is more metadata, and metadata is maybe even more relevant to gain some transparency, let's say, in the management of this distribution and the different challenges it poses. Okay, so again, if we go from some abstraction level, again, we have same storage as before. Now we have processing, which is somehow, okay, fine, divided into a global and local, but it's processing in the end. Then we have some querying mechanism. And then, as I said, there is metadata that starts gaining some relevance in this kind of architecture. Okay. So now our proposal is to go a bit further in this sense. So as you will see, we will end up from some abstraction level, we'll end up having the same component, but now we advocate for some big data architecture. In this case, that we have our batch layer here based on this Lambda architecture. This would be the batch layer. This would be the speed layer coming from the Lambda architecture. Then we'll have the serving layer, we said before, but now we have also some semantic layer for this metadata management that we already know that is especially relevant in distributed systems. Okay? So the idea of this architecture is that we have some data that is coming in the form of a stream. So then we have some dispatcher that deviates or decides which data is going to be stored in our data lake and which data is not going to be stored in our data lake. So this data is kind of filtered out somehow, or just simply decided not to be stored for further use. Other data can come directly to the data lake, so in batch mode, not from the stream. Then at some point, independently of whether they come from the stream or from batch, we will take this data and we will create some statistical model, some function, if you want to see it that way, and this will be stored in our metadata repository. Okay, so all these models that we have, when new data is coming through the stream, will be applied to this data, and then this will be a classifier, could be a regression, could be whatever. So this would be moved to the serving layer, and then eventually our users will come, will search for some information, and then would find the result of the application of these models, and they will get these results of the application of the machine learning. Okay, so this is basically the idea of the architecture. So as you see, we have the storage as before, in this case in the form of our data lake. We have the processing as before. In this case, we have both branches, the batch and the real time, let's say the stream processing, and we have the querying as we had before. And now what we have is the metadata, which is in the center of the whole system. And what is left here is something that appears because of this variety and variability of data and having external sources in the case of big data architectures. So we need some ingestion, or ingestion is getting more relevance in this case. Okay, and then also to manage all this system, since as we are going to see now, we will need some many different tools. We need some coordinator, let's say, as well, or orchestrator of all these tools that we will see. Okay, so here you see, for example, these are some examples of the tools that you can place in the different components of this architecture. Okay, HDFS or HBase, Mongo Flink, Spark Streaming, Flume Kafka, whatever. I'm sure you're familiar with all these, but this is just different ways or different roles that we need to cover if we want to have an architecture like this. Okay, how we can instantiate all these components with pre-existing tools and avoid getting this spaghetti architecture that I mentioned before. It's just a way of putting some order, let's say, on all this. Okay, so this is from the point of view of the components. Now, from the point of view of the use, so how can we use all these tools? So now the tools are already there. Now we need just to somehow configure, or we need to govern this data and metadata that they are managing and they are requiring. Okay, so in this system, how can we use? Okay, so this is our system with the different components from this high level I said before. So let's start paying attention to the storage and somehow as well to the ingest. Okay, so we are focusing on this part of the architecture, and since the metadata is in the middle of all these, because we think that it helps in the management and the semi-automation of all the tasks. Okay, we'll also see what happens with this metadata. Okay, so then what we have here is, okay, here we have the ingestion of the data, okay, with the different sources and so on. And the first thing we need is some landing zone, I mean, to receive the first files. And for this we have some temporal landing, let's say, with purely files, so where some users can simply upload these files, and then we would perform this pre-processing, this registration of the sources, and then extract some of the metadata, some schema, and start producing some mappings, etc., etc. This would take us to some formatted zone, which would be some common format. So in the landing zone, we could have CSV files, we could have JSONs, we could have whatever. So in some sense, I mean, to facilitate the life for our users, we should come up with some common format that could be JSON or it could be whatever. Okay, and then we could also decide some fixed transformations common to all the analysts, so common to all the companies, to any project in the company, and this would give us some trusted zone, trusted in the sense of some basic cleaning of the data common to everybody, and then from there we would move to some exploitation zone that we put available all these, I mean, relations, data frames, tensors, matrices, whatever for these analysts, and then here we could plug this whatever, I mean, OLAP, query reporting, notebooks for more advanced analytics, etc. Okay, and then here, this is the point, we have all the metadata artifacts we need to manage all this. Okay, so in the end, what we have is here our raw data, okay, just organized by source, the versions we could have of these files, etc., etc. Then here we have some systematic storage and metadata extraction of schemas I mentioned before, okay, which is the structure and the content of these files, and then we should come up with some canonical common model for everybody, and some project independent, as I said, kind of traversal to the whole company cleaning of the data, and then some semantic homogenization and integration more for every project or for different views we want to offer to our users. And then in the side of the metadata, I mean, we need to automate some transformations and processes, etc., with these mappings, and then we monitor as well the flow of the execution between the different zones, the different transformations we are performing, and then in the end we need to manage the schema and the data views, etc. Okay, and then also we could add here profiling, traceability, and other tasks that need to be done in this context. Okay, so if we go back to the architecture, what happens now with the analytical part? So it would be related to the processing and also related to the query. And as before, I mean, of course, with the support of the metadata. Okay, so then in this case, starting point is the exploitation zone that we had in the previous slide. Okay, with the relations, data frames, tensors, etc., etc. From there, every project or every analyst can have his or her own analytical sandbox where they can play with this data, and then they can perform some feature engineering or whatever transformation they require to, in the end, create their models. Okay, so then they train the models, and in the end they validate the models, and when they are satisfied, they move this into some production environment where this can go to the final applications and the final users. And the same as before, here we have all the part of the metadata and the data governance, etc. Okay, so again, here we have subsets of the relevant elements for this project, for this specific analysis or goal. Then we have some feature engineering, labeling of the data, etc., etc. So here we have the running of the machine learning algorithms, and then in the end we deploy this in production. Okay, and then at the side of the metadata, again, as in the previous case, we have to automate all these transformations we have between the different zones and the different data sets, and of course, monitoring the flows between the different zones, just to keep track of where things come from, etc., and guarantee this traceability that I said before. And then we need to manage as well the different versions of the different machine learning models, for example, that have been created. Okay, and then finally, if we go back to our bolster architecture, what is missing, let's say, is okay. Let's focus now on the metadata itself. Okay, on the metadata management and governance itself. Okay, so for this, what we think is that we need some kind of system which is here in the center, and that actually interacts with the sources on the one hand, and then the execution engines, and through the engines with the storage systems. But we see some specific tasks that or submodules for the metadata management, and then of course some metadata repository. Okay, so here, first of all, one of these modules is in charge of the integration. So for this integration, as I mentioned before, we need to create some wrappers for the sources. So we need to design these wrappers, and in the end create these wrappers that would be stored in our metadata repository. Then we need to extract this schema, and for this we advocate for the use of knowledge graphs, and then another knowledge graph that would be the global integrated schema, and then of course the mappings between the source graphs and the knowledge graphs as well. And all these would be done with some module in this metadata management system, let's say, which is part of the bigger big data management system. And then another module would be the query manager in this case. So we need to, using this global graph and the mappings, we need to rewrite our query in terms of the sources, and then this goes to the wrappers and the source graphs, and then we would be able to create a flow that actually goes to the sources, extracts the data, etc., etc. This would create, as we saw before, our data intensive flow, which, as we saw before, again, it can be extended with some palette of data cleaning or improvement tasks. And then in the end, we should choose which is the engine that we want to use. That can be, as I said, Spark or Flink or whatever. Okay, and then in the end, this goes to some of these to the selected engine in this case. Okay, the other module would be more related to the guarantee of the data quality, as we saw before. We need to detect potential errors, or in the end, we have some rules or integrity constraints, and thanks to this, we evaluate the quality of our data sets, and then we potentially, have a palette of transformations and apply these the transformations for preparing the data, or because they need some transformation for some specific purpose, and then we come up with some modified flow, and then in the end, it's the same as before. We need to select the engine, and then this would go to the concrete engine for execution. Okay, and then finally, the last module in this metadata manager would be the data flows themselves, the one managing the data flows. So when we want to go into production, just deploy these flows into production. In this case, we need to consider some service level agreements in terms of whatever kind of cost or constraint we want to impose in terms of execution time, or whatever. We need to consolidate the different flows. We may need to decide which is the format we need of the storage or of the processing or whatever. We need to select some materialized views to speed up the process. And then again, we have the selection of the the engine, and this would go to the engine, and then finally this would be executed in the storage systems. I mean, would be executed. I mean, getting the data from the sources here, you get the data to the sources, and then this data would go to the views that in the end the user here can query. Okay. So just to close the presentation, what we have seen is that there are some specific tasks for data engineering, that these tasks cannot be achieved simply with a relational DBMS, even if some of them kind of have the same purpose. Still, we have new challenges based on the volume, velocity, variety, etc., etc. So for this, we need to consider well-known techniques, which are the data lake, the Lambda cap architecture, and so on. And our claim here is that it is harder if we try to do this all manually. So we need some kind of automation. We don't think completely automation. I mean, complete automation is feasible, but at least some automation is desired and is possible. And this means that we should be using metadata in this case. Okay, and for this, what we propose is this bolster architecture that in the end follows kind of the same principles of a relational DBMS architecture, the different components for storage, processing, querying, metadata management, etc., etc. Okay, and then in the end, this query, which is the system for the management of the metadata with the different modules, again, for definition of the mapping of the sources and the queries and also the quality and the deployment in the end of this flow. Okay, so if you want to read more about this, basically most what I presented, I think it should be in this publication here and in this publication here. So this is all I wanted to explain. So if you have any question or comment, I will be happy to answer them.
Well, thank you, Alberto, very much. It was a very nice, interesting presentation. I think it you managed to explain very well the complexity that is underneath these kind of systems and all the challenges that ultimately we need to face. I have a comment to make, but I'm gonna let the audience start. Well, I see first the raised hand from Micah. So please.
Thank you very much. And thank you for the very interesting talk. In my opinion, it's very interesting to have this trusted zone as an additional component that is not available in distributed databases, especially because of this NoSQL data. I have seen that rules shall help to validate the data. Can you give some more details? What can be checked and what you can realize for mapping data from the unified view into the trusted zone? How can you validate data?
Yeah, I mean, the first thing you can do, for example, is to fill gaps, let's say, or to complete missing values, etc. Okay, but more specifically, for example, what we are working now is on crossing different sources. So when you have different sources, sometimes they have kind of complementary information, in the sense kind of a lookup table or whatever. But in other cases, they are overlapping sources with different views of truth. Let's say, I mean, there is not one single truth, but there could be different truths in this case. And then what we are working now, and we will be presenting this in DOLA, by the way, this afternoon, is a system to cross these sources, and in the end to decide which is the single truth, if you want, or how far away each one of the data sources is from the single truth, if we assume that there is a single truth of this. So this is something that could be done in this case, this evaluation of, in the end, the data quality or the different views they provide. Okay, this is related to record merging, for example. You know, this would be one thing that we could be doing there.
Thank you very much.
Okay, then I see Panos. Hi, Panos.
Hi guys, nice to see you all there.
Hi, nice to see you, Panos.
Sorry I was not from the beginning. This is teaching day for me. So this is just, I popped up a little bit in the second half of the talk. So I just have a very high level comment before I leave for class again. It seems a little bit too complicated, Alberto. I mean, by seeing the entire architecture, it reminds the following. It says, data warehouses started becoming a little bit more not popular exactly because they started becoming more and more complicated. And here we have landing zones and processing zones and cleaning zones and merging zones, which I understand they are necessary. But at the same point, there is an overhead. You have to administer them. So I don't know what is your experience with this, because I would expect that this becomes huge and complicated, and maybe you have thoughts for simplifying somehow, or saying that we can take some kind of modular approach where we can leave out this part because we don't need it in this case. I don't know how this should work. So
yeah,
just
I fully agree. I mean, you're right. This is not trivial, let's say, but the alternative to this, for me, is even worse. Let's say, so if you just leave individuals, I mean, one analyst to work by himself or by herself in the different sources and just create their own flows and the different notebooks and whatever, and then other analysts do the same, and everybody does the same on their own, then I think it's a mess. First of all, it's more expensive and it's less reliable. Okay.
Oh, sure.
So I agree with you that this is not trivial. This is not easy. And of course, maybe we can skip some of these zones. Maybe some of these are not necessary in some cases. Some can be overkilling solutions in some smaller companies or more less demanding situations, let's say. And this is kind of a reference architecture, especially in the sense that they are saying, facilitating all these difficult, overwhelming tasks, let's say.
Okay. Yeah.
So what we are not saying is that you need exactly all these in all the cases, okay? But the alternative for me, it's not clear to me that in the end it's easier if you just let. Of course, we are not talking about one single analyst in an SME. Okay, we are talking about a relatively big company with a relatively big team of analysts.
Okay. All right. Thanks. Just a quick thought. I have to fly for the course, so I hope I will see you in the afternoon, guys, later. So
Sure.
Thanks a lot. Bye bye.
Bye. Thanks, Panos.
Bye, Panos.
Stefano.
Yes, so first of all, thank you, Alberto, because you gave us a very comprehensive view of the process of the architecture. Yeah, I agree with Panos, it's a little scaring actually, but because of the huge technological stack you have underneath, but I also agree that this is actually necessary, so okay. I have two questions, actually. One is more general, and the second one is maybe related to what Panos said. The first one is, okay, we agree that there is a very important need for metadata. So, okay, management and so on. But do you think that, are you working to create some meta model? Or do you think that each data steward will have to create her own meta model with her own concept? So the question is, do you think that there are some reference concepts, some basic concepts that you should make available to all the users and analysts and data stewards for populating with the specific data they are working with? Or do you think that it's up to each single project to set up from scratch their own metadata?
No, I mean, of course, I mean, there must be some standardization, let's say, and some common concepts to everybody. But for me, so let me do another parallel that maybe I didn't mention, and I think it's important. So in a relational DBMS, we also have a catalog, right? So the content of the catalog is metadata, and you don't have a different catalog for every instantiation of Postgres or Oracle or whatever. I mean, the catalog is the same for Postgres always. The catalog is the same always for Oracle. And maybe in some other cases, you have some other metadata that you require, or maybe some of this metadata in the catalog is not needed in some cases, or whatever. But the standard catalog is there, and it must be there.
Okay, but are you working in this direction, or?
Yeah.
Ah, okay.
Yeah, we are trying to define already something in this line. Yes.
Okay, good. And the second question is, well, you know that now multimodal DBMSs such as Postgres are emerging somehow as a way to give you some transparent view of heterogeneous models. So do you think that adopting some multimodal DBMS could be one way to hide some of the complexity in a data lake architecture? Because with this sort of DBMS, you will be giving to analysts and users some sort of a unified view for querying, for instance, because you can query data, NoSQL data with different models using one single query language. So do you think that this can be a way to relieve some of this complexity?
Yeah, I mean, I mean, you are a bit older than me, you know, so maybe you
well, thank you for reminding me.
So maybe you live this. I mean, the pre-relational years, no, more in the 80s and so on, how it was. So for me, I didn't really live all that as I mean, in first person, let's say. But for me, I think the situation is quite similar. No, so in the end, you had then different models. I mean, hierarchical, network, and then relational, and simple files, and so on. And then in the end, there was one single DBMS and somehow hidden all the complexity underneath. No? So for me, we are kind of in the same situation. We have different models, and then eventually, I don't know if it will not be next year, but maybe in 5-10 years, I don't know, maybe more. I think we will end up having one single system that hides all this complexity from us, and we can call it multimodal or whatever. But I think, yes, I think this is what will end up happening. Let's say that we need to abstract. I don't think this is, in the long term, I don't think this is sustainable, dealing with all these different tools and just creating projects from scratch. Let's say these very few companies are big enough to handle this, or have a strong IT department to handle all this. Most of the companies, their main purpose is not IT, so they are not going to spend all the money in this department and in these human resources. So they want something more kind of off the shelf, you know, just install something and then it hides and underneath you have whatever. I mean, relational, you have JSONs, or you have whatever, and it is automatically managed for you.
Okay, I just want to emphasize that when the relational model came out, I was just a child, actually. But okay, that was not exactly the same thing that happened, because the relational model actually wiped out the hierarchical model and all the others, while in this case, they are trying to let them live together under the same hood, let's say. But okay.
But in the end, what you have is, I mean, XML types or JSON types inside the relational DBMS.
Yeah, that's true. Yeah, in Postgres.
I know it's not exactly the same, but I find many similarities.
Okay, thanks.
I would say last question from Patrick.
Yeah, I was just going to ask if we have some time. So it's the question is going to be quick, but the answer, I don't know. Thanks, Alberto. Hi, Alberto, and thank you for this very interesting talk. Maybe I missed it at some point, but you know, these days there is a big tendency in the data management community to towards machine learning. So now you can learn indexes, you can learn many things, and it turns out that probably it's going. I mean, I don't know. Maybe the next data management platform is going to be fully driven by machine learning. So I would like to have your opinion on that in the architecture, in the vision that you are describing. How machine learning could help? What is your opinion on this tendency? And well, if you have an opinion.
Yeah. No, of course. I mean, you're right. I didn't enter into how to implement this. I mean, my point was just I just wanted to make the point or raise the attention, let's say, on the need of these tools. Now the question is how to build these tools, so this metadata management system and all this governance of this metadata and all the generation of these wrappers, or the generation of the mappings, or you know, all these. So enacting in the end, implementing all this. So in the end, I see machine learning as a way of programming as well. Let's say. You can develop by programming in whichever language, or you can develop just by giving examples and then letting the machine to learn how things should be happening. So for me, just an alternative of development, and if you have the right data, a more efficient way of developing, most probably, and then in the end you get results as good as those of a programmer, or even better than those of a programmer. So it's always an alternative for development today, I think, clearly.
Thanks.
Okay, well, I guess we're out of time, okay, and out of questions again also. So again, Alberto, thank you very much.
Thank you.
My pleasure. Thanks for the invitation.
Yeah, and okay, so we can start with the next session, and I'm not sure whether I actually see someone from to present Unidata. Is there?
I'm sorry, can you hear me?
Yeah.
It's going to be me, because sadly none of the co-authors of the paper could be here, unfortunately.
Okay.
Present for them.
Okay. So please, Anna.
Okay.
You can share the screen. Yeah.
Sure.
If you just connected, just
no, I've been here the entire time.
For the entire? No. Okay. So you know we've been recording the session, right?
Yeah. Sure.
Okay. Perfect. Please then.
1 second. Can you see my slides?
Yeah, we do.
Yeah.
Great. So hello, everyone. My name is Anna Smirnova, and I'm going to present our product, the Unidata platform. This system is a result of collective effort of many people, some of whom you can see on this slide. Obviously, I'm not Alexei, but unfortunately, he couldn't be here, as I said. To start off, I should say some words about MDM and what it is. Well, it's obvious that nowadays companies and public institutions manage huge volumes of data, and it has become a strategic asset. At the same time, each organization usually possesses a complex data ecosystem, which makes it hard to make use of information contained in it. Efficient data use requires much more effort, such as ensuring data quality, tracking data lineage, setting up ETL pipelines, and so on. Master data management solutions aim to address these technical issues by consolidating available information while interacting with existing systems in a minimally intrusive way. Master data, in turn, is all kinds of data assets important for continuous operation of a specific organization. For example, it may be customers, inventory, employees, and data sets specific for this organization. As a research discipline, however, MDM is an actively developing area that concerns all aspects of enterprise data management practices. Its practical counterpart is closely monitored by Gartner, as it is well known, which releases early reviews describing established and promising products. And also there is the fundamental reference which describes all aspects of MDM called DMBOK, which has been recently published in the 2nd edition. So starting off with MDM adoption, during MDM adoption, information systems are integrated with the MDM solution. And there are 4 important points to consider. First of all, the structure of large organizations is usually the result of historical processes such as acquisitions and mergers. And the same goes for their information systems. One of the results of this is a unique software ecosystem comprised of core technologies from various vendors. Next, multi-domain MDM is the state-of-the-art approach. And aside from generic domains such as products and vendors, there may be business-specific ones, such as patients for a hospital, for example. And finally, there are various external constraints which an organization has to follow and which define the structure of the business processes. So as for the actual adoption, there are 2 popular approaches, technology push and organization pull. Technology push is a large-scale adoption of a new technology based on the belief in its usefulness. In contrast to that, potential customers of MDM systems need to solve particular tasks. This is what can be called organization pull. This approach significantly reduces the costs of MDM adoption compared to technology push. The primary reason for that is the narrow application area, and moreover, its iterative nature enables progressive buildup of MDM functionality by a step-by-step incorporation of different business areas. Finally, what I need to mention is that the need to fulfill specific tasks leads to a specific approach to creating an MDM solution. It leads to a subset of the MDM functionality being clipped out from a general purpose MDM toolkit. This can be due to various reasons, such as adapting to the existing software ecosystem, for example. So therefore, implementing MDM in the organization pull manner requires the underlying MDM toolkit to be highly flexible. And this is exactly our case. The Unidata platform is the core technology of an industrial product line that was used to produce dozens of target MDM solutions for large organizations. These solutions are focused on the specific needs of organizations, such as specialized business segments and heterogeneous IT infrastructure. The platform has received an honorable mention by Gartner in the Magic Quadrant for Master Data Management Solutions 2021. The architecture of the platform aims to address the concerns mentioned on the previous slide. On the right, you can see the core idea of our approach. Basically, that it is a kit of Lego building blocks. And on the left, you can see the core principles that our platform follows. First of all, it's tunability, meaning that an MDM platform should be really adaptable to various software ecosystems, as I've already mentioned. Take into account specific priorities and issues of the concrete business and comply with external constraints. This will ensure that target MDM solutions meet their organization needs. Next, it's component-based architecture, meaning that the platform should consist of modules which can be freely combined together in order to create efficient and specialized solutions. And finally, meta-modeling. Meta-model describing models of individual areas can be used to handle combinations of different domains, and this will provide the product with extensionability also. I think it's worth mentioning that the core set of Unidata modules has been released as open source, which can be seen by the link. So next, I probably should mention some and present some core concepts of master data management. I've already said that what master data is. They are core business objects with their metadata, attributes, definitions, roles, connections, and taxonomies. And MDM is a set of practices and information management methods and data management tools, which are used to, well, manage master data. The formal definitions are provided in the paper. Next, what we call a golden record is essentially all available information concerning a particular entity. Next, meta model and data model are the entities that are required in order to support a particular domain. The objects which the platform works with must be defined, and the meta model is the description of the data itself, the schema, and related procedures. And for example, as an example, a meta model is a supplementary meta model of data quality for a domain. A registry in Unidata is a collection of records that are related to some entity obtained from different source information systems. And a lookup table is a referential table that contains data which is rarely changed, but at the same time frequently used, such as time zones, for example. Next, system of a record, it is a primary data source which contains the true value used in cases when an attribute has different values in different source information systems. This is the concept. Concerning the technical implementations of MDM, there are 4 widely used styles. You can see them in the picture over here. They're different in interaction patterns between source systems and stored data. For example, in some cases, data cannot be copied or moved for various, including legal reasons, and we must store only corresponding references. And all of these styles are, of course, supported by the Unidata platform. Concerning the role of humans in MDM systems and Unidata, they, of course, require a data steward, which is kind of obvious, but however, in practice, as we noticed, a data steward is not necessarily a single person, but rather a group of several people. In the Unidata platform, as well as some other MDM systems, support 2 types of users that carry out data stewardships are supported. It's an administrator, this is the person who manages the platform in general. Their duties include data model administration, classifier administration, and managing rules of duplicate detection, and so on. And a data operator, this is someone who manages records and performs database population of databases, registries, and lookup tables. This is the person who participates in all related business processes. Next, to give you some specific examples what this is all about, and to also demonstrate the organization pool aspect, I will now briefly talk about 2 of the projects completed using the Unidata platform. However, our paper has a much longer list. So the first use case is a classic one. It concerns development of a product catalog for a large telecommunication company. The goal was to consolidate a large variety of information, namely information regarding product offers for different customer segments, information related to service availability, financial information from the billing system, and accounting records. As a result, a product hierarchy, or just a product tree that contained various product details, including financial ones, was constructed. It's now utilized by the sales department and financial officers of the company. The second use case reflects the focus on a particular task, meaning this organization pool approach. The aim of the system was to find clients in the client database that had so popular social media accounts and a lot of followers. The company wanted to improve their loyalty by offering additional discounts and privileges, and in order to obtain also more customers from their follower bases. The core data governance tools that were used were data enrichment and data consolidation. Now turning to the architecture, you can see it depicted as a diagram here. I'd like to discuss the 3 basic entities. The platform consists of modules. A module is a self-sufficient set of functionality that is intended for solving a particular problem. Each module contains a number of services that cover parts of this functionality. For example, the meta module, which encompasses all metadata-related activities. And it contains services that cover, for example, managing lookup tables or registries, etc., etc. Modules have rules of creation, behavior, and they also can interact with other modules while being a part of a pipeline. So a pipeline, in a broad sense, it's a sequence of operators which are performed either on data or on the model. Pipelines implement data flows, which consist of service calls and may contain utility nodes, such as branching, calling out the pipeline, and so on. Thus, modules and pipelines implement tunability and the composition aspects that discussed earlier. Finally, components, which are essentially groups of modules that have a related purpose, and there are 4 of them. First of all, platform core contains basic modules that implement core services of the platform and minimally depend on other modules, such as system boot, job batches, and data types. Next, storages concern everything related to data stores. And these modules actually abstract functionality required by the platform from the specific DBMS that underlying DBMS, and restrict and simplify it, because usually not all functionality of a DBMS is required. Next, the MDM component includes all modules that implement basic MDM functionality, such as metadata management, rules for computing master record alternatives, data quality management, duplicate detection, and so on. This component is responsible for integrating and synchronizing all necessary data stores that reside on the previous level. And finally, extra MDM implements advanced MDM functionality and contains modules that are either advanced variants of some existing module from MDM, or modules that provide functionality usually implemented outside of MDM. Due to the time constraints, I will not be describing individual modules. Well, some of them are listed and described in the paper. Speaking about implementation requirements, however, first of all, these are tombstones, tombstone deletes. Information should be deleted only when it is absolutely necessary. And real deletion should be performed only by an administrator, where regular users should not actually delete data. It should be marked as deleted, and the system should take this into account when just a user deletes it. Next, version and support should be pervasive. Users and administrators should be allowed to reconstruct previous versions of any object. And at the same time, querying using validity periods, which is discussed further, should be supported. Finally, provenance, meaning traceability, should be provided for any operation. For example, if a bulk loading operation inserted records into a database, it should be possible to reverse it by removing the inserted records and keeping the rest. Next, let's see how the users interact with data, can interact with data with validity periods. You can see on the picture an example that concerns St. Petersburg, my home city. During its history, it was renamed several times and depicted, the data depicted here. Suppose that we're building an MDM system where information flows in parts. First, we only know that it was called St. Petersburg since it was founded in 1703, and the blue line depicts this, as you can see. In 2019, however, we learned that there was a period when it was called Leningrad, so we add the red line, this one. And the same idea with another name, Petrograd. We add the yellow line between 2020 and 2021. So basically, there are 2 dimensions. As I've already shown, the x-axis, which is the validity period, and the y-axis, which is the fact arrival time. We should not overwrite any of this data, because we should always serve any of the possible queries which may arrive. Let's consider 2 example queries, 1 and 2, represented by these little numbers. The first one asks what was the name in 1920 according to the system now in 2021, and the number 2 asks the same question, but according to the system in 2019, and the output answers should be and will be different.
Sorry, Anna, to interrupt, just to let you know that you've got, well, 5 minutes left.
Oh, I'm sorry. Okay, I'll try to be faster.
Thanks.
How is this the data stored inside the BMS? There are 3 core tables, which you can see: echelon, origin, and history. They share attributes, and they are interlinked by primary key foreign key relations. Echelon is the metadata of the golden record. Origin is the metadata related to the system of the record from which the record originates. And history, well, version history is the validity period shown on the previous slide. Their attributes are described in the paper. I'll just mention that data B's here is the data itself in binary form, and here is the borders of the validity period, valid from valid to. Everything else is, of course, described in the paper. Next, this is about, I'm going to finish very soon, but this is a bit about query processing. Is that suppose we only have one source system and we must find an answer to a query. What was the name of St. Petersburg at some moment X according to system knowledge at the moment Y? We must construct validity periods out of the history mentioned previously data. This is done by pairwise intersection of all entries in the history table that concerns the same entity. An example is presented, as you can see. Here are the periods. Here is the calculation. You can see the updated valid from valid to and in one. This way, the correct record is selected. But what if there are several source systems and there is a conflict in an attribute? There are two algorithms that can be used for this purpose: best value record and best value of the truth. They're described in detail in the paper, and due to the time constraints, I will only briefly outline the idea. First, we, of course, calculate the validity periods. Then in steps 1 and 2, we select appropriate candidate records that contain different values. And on the third step, we select them from the record. We select them from the record from the source system with the maximum weight. This is the BVR. The BVT is very similar, but it treats null values differently. And there's a separate set of ways for each attribute, which is not present in the BVR. Finally, this is the last slide. Despite recent significant technological advances, human approaches to handling information have not really changed. And this is also true in case of MDM systems, in which interaction scenarios have stayed the same. Users still have to think about data layouts and procedures and define registries and referential tables, set up data pipelines, and so on. In other words, people solve problems in an imperative way, specifying everything that needs to be done. At the same time, humans think in terms of problems such as, why did sales drop in the last quarter? So a declarative approach could probably suit these problems better, and there's a need for it, or at least try it. And there are several promising approaches. For example, exhaustive standardization, which is very challenging since there are too many details that should be reflected inside the standards. But machine learning, on the other hand, will incur smaller costs and will not depend on any external collaboration. And a fully fledged AI with a natural language interface is a very distant vision. There has already been some successful adoptions of machine learning in individual components of MDM systems. For example, for semantic column type detection, for database schema matching, duplicate detection, and table autocompletion. Another promising direction is digital storytelling. Its idea is to automatically extract and present facts contained in the data in a human-friendly way. Employing such techniques can lower the qualification requirements and open analytics to a broader public. And finally, there's also a novel class of the so-called visual analytics systems that contain collaborative tools that allow users to employ various visualization primitives, machine learning models, and other objects. These are dragged onto a dashboard and connected to each other in order to construct pipelines. And thus machine learning will be present not only inside such systems, but outside as well. Thus, it will allow users to use custom machine learning models inside their decision-making pipelines. So I think that is it. Thank you for your attention. I will be happy to try and answer your questions. I'm out of time.
No, we're good. Thank you, Anna, for the presentation. I see a couple of questions. Okay, so, well, Stefano raised his hand first, and I don't know.
Yeah, well, it was actually close, but I also have a question.
Sorry.
So, Okay, Anna, my question is, if you can just go back to slide 6. There were
meaning the number. This one?
Yeah. There were two activities or process there, consolidation and harmonization. Could you just briefly explain what's the difference between these two?
Oh, yeah, sure. Just a second, I'll get my notes and tell you. You were asking about consolidation and harmonization, right?
Yeah.
So the other name for harmonization, I think it's centralization, as can be seen by the picture. So maybe it's a more intuitive kind of name. Well, in consolidation, as you can see here, data is uploaded into the common repository, this hub, on a regular basis, then is processed, and then the hub itself provides data consuming systems with access to this data. However, new data is supplied by live data source systems. And her centralization or harmonization is very similar, but here the hub takes over the data upload as well. And then basically all systems that were initially data sources are turned into data consumers, as shown by the little arrows here.
Okay, thank you.
Any other question from the audience? I just have a very quick one. I think it's the next slide where you talk about human interaction. Okay, and
right.
so okay, so here you talk about two roles: administrator, which is more at the governance level, and operator, okay, which works at the individual records. I was wondering whether the platform, or whether it does, or if you envision a more comprehensive interaction with users, especially in terms of metadata, okay, because gathering metadata is quite challenging, and I think that the interaction with human can help in provide additional information concerning the data sets and the processes and so on. So I was wondering if it's something that the platform does, or if it's planned.
I'm sorry, I don't. Could you please?
Okay. The question was whether the platform provides some more advanced functionalities in terms of interaction between humans and platform, or other than the ones described here, or not.
And you mean in terms of data stewardship, or just everything else?
Everything else.
Well,
okay, maybe that's something for the authors of the.
Yeah, maybe that's something for people who implemented the platform. Yeah. I just know the theoretical parts of this. Sorry, but at least I know that the paper does not mention anything about that.
Okay, thanks. Okay, if there is no other.
There is an answer on the chat. Georgie says managing metadata is administrator duty.
Okay. Yeah, George is the co-author of the paper.
Okay. Thanks. Okay, I think we're done for the first session. Now, before we break, let me just say that one thing I forgot to say before about the proceedings. We've been informed this morning by the workshop managers that they're going to be published after the conference. Okay. Okay, let's take a break, and let's meet again at 11 British Summer Time, or 12 Central Eastern Time, Central European Time. Okay. So in 25 minutes. Again. See you later. Okay, recording now in progress. Okay, Matteo, up to you.
Okay, so hi everyone. Nice to be back from the break. So the next paper is RTGen, a relative temporal graph generator. And I think the speaker will be Maria, right?
Yes.
Okay, so I leave the floor to you. You have 15 minutes, including question and answer. So let's try to make it in 10 or 12 minutes. Thank you. So the floor is yours.
No, sorry, man. This is actually 25.
Oh, sorry. Yeah, it's a long paper. Yeah, 25. 25. So yeah, you have more time.
So 20 minutes for the presentation and 5 minutes for the questions, right?
Yeah.
Okay, thank you so much. Okay. So can you confirm that you can see my screen?
Yeah, we can see your slides.
Yes, very good.
Okay. So hi everyone, my name is Madia Massi. I'm a third-year PhD student. Thank you for organizing DATAPLAT workshop. It's a pleasure to be part of it. Today I'll be presenting the paper RTGen, Relative Temporal Graph Generator, authored by Zoltan Miklos, who joined us today, Philippe Répin, Pierre Meillet, and myself. This work is a collaboration between Orange Labs and the University of Rennes 1, France. In this work, we are particularly interested in data sets used for the evaluation of graph-oriented data platforms. Usually, real-world data sets are inaccessible because of confidentiality agreements or do not fit the scale requirements. Hence, practitioners tend to generate their own data sets. Those data sets mimic the characteristics of real-world data sets, or particularly real-world graphs that are controlling the degree distribution, community structure, and the clustering coefficient. Now, real-world graphs are dynamic in the sense that nodes or relationships can join or leave the graph at any time instant. Examples of such graphs are transportation, citation, or sensor network. And now, a recent analysis of the evolution of such temporal graphs paves the way to anomaly detection or forecasting the future behavior. Hence, a recent interest has been steered toward designing data platforms that can manage temporal graphs. And hence, more particularly, recent interest has been steered toward generating temporal graphs, which constitutes the main motivation of this work. Here's the outline of the presentation. First, I will discuss the related work on the generation of graphs, and particularly temporal graphs, and provide the limitation. Then I will define some preliminaries needed for the understanding of key concepts of our proposal. After that, I will provide an overview of our generation tool, RTGen. After the overview, I will discuss more deeply the relative graph generation procedure. Then I will present the evaluation results of RTGen, and finally, I will conclude work and provide a future perspective. For the related work, an extensive study has been posited on the generation of static graphs by controlling key features of a graph, such as the degree distribution or the community structure. Now, temporal graph generators, however, have received much less attention, such that available generators propose or present limited capabilities, such that they generate growth-only graphs with no deletions, or they present simple graph updates, such as flipping the direction of edges. And more importantly, they do not control the evolution of the degree distribution or the community structure, which motivated us to propose and implement RTGen. Now, the first preliminary is the degree distribution. So what's a degree of a node? The degree of node is the total number of edges or relationships connected to a vertex, and the degree distribution is the probability distribution of degrees over the entire graph. Now, the Changlu's model was proposed for the generation of random graphs with any given degree distribution. It consists of assigning each vertex with a desired degree, and then after a sufficiently large number of added edges, the actual degree of each vertex approximates the given or the expected degree. The second preliminary is the community. Now, how to define communities? Unfortunately, communities cannot be quantitatively well defined. However, one can intuitively define a community as a group of vertices that are more densely connected between each other than they are with the rest of the graph. And now the stochastic block model is used to generate random graphs with any given expected community structure. It consists of defining a stochastic community matrix M, whose elements MIG represent the linkage probability between community CI and CG. And then based on the stochastic community matrix and the stochastic block model, the generated or the community density of the generated graph approximates the stochastic or the given stochastic community matrix. Now, inspired by the previously described generation models, the Changlu and the stochastic block model, we proposed RTGen that can generate or produce a sequence of temporal graph snapshots, such as each graph snapshot approximates given degree distribution and community structure. Hence, as an input, the user should provide the parameters of the evolution of the degree distribution, the number of vertices in each snapshot or in each time step, the number of time steps or snapshots, and finally, a stochastic community matrix to define the community structure of the generated graphs. The output of RTGen is a sequence of graph snapshots such that the obtained degree distribution and community matrix of the generated graphs approximates the ground truth parameters. Now, our relative generation procedure consists of generating a new graph snapshot GI based on a previous graph snapshot GI-1 after applying a number of graph updates. So first, we need to morph or to transform the degree distribution of graph snapshot GI-1 into the degree distribution or the desired degree distribution at time step I. To do this, we need to compute a transportation or a mapping matrix and then assign vertices with degree variation. And then after applying all the degree variations of all the vertices, we obtain a new graph snapshot GI whose degree distribution approximates phi GI. Now I will describe more deeply the relative graph generation procedure. So first, to be able to transform the source degree distribution Phi-1 into target degree distribution Phi, as I mentioned, we need a transportation matrix. However, temporal graphs tend to gradually evolve. Hence, this transportation matrix needs to minimize the effort of morphing the degree distributions or in other terms, to minimize the number of graph updates between two successive graph snapshots. Two successive graph snapshots. Hence, we used or we referred to an optimal transport solver. The optimal transport solver computes the transportation matrix gamma given a source and a degree and a target degree distribution and a distance matrix D that defines the distance between the source and target distribution points. To clarify, on the right side illustration below, the element 50 of the transportation matrix implies that 50 nodes in the source graph Gi-1 having a degree 30 should have a degree 40 in the newly generated graph snapshot I, hence a degree variation equals to 10. Now, once we obtain all the degree variations of all the nodes of our graph, we also assign each vertex with a linkage probability by changing the linkage probability of the Chang-Luz model. So instead of defining it as the degree or expected degree over the sum of all the degrees, we defined it as the degree variation over the sum of the degree variations of the graph. Now, as we can see on the toy graph example, after applying the updates, the new degree of each vertex is equal to its original degree plus the degree variation. And now our second goal was also to be able not to control only the evolution of the degree distribution, but also the community structure. Hence, we distribute vertices into communities, and then we define a degree variation for each vertex in each community. Now, the new linkage probability or the community-aware linkage probability represents the probability of linking a vertex belonging to a community CM. This probability is equal to the product of the probability of picking first a community, and then the probability of picking a vertex inside that community. Now, by replacing the sum of the degree variations in each community by this formula, we reobtain the original linkage probability. This duality allows RTGen to control both features. First, the evolution of the degree distribution, and second, the community structure. Now, as we mentioned, RTGen takes as an input a stochastic community matrix. However, we also provide an auto-filling procedure such that the user provides the characteristics of a hierarchical community structure, such as the depth or the height of the tree and the branching factor H and B. Besides, we also propose a tunable parameter K that is proportional to the difference between the within and between linkage probabilities. K will be discussed more deeply in the evaluation slides. Now, to evaluate RTGen, we produced or generated a sequence of graphs with different input parameters. The first set of parameters defines the evolution of the graph or a growth-only graph with a Gaussian degree distribution. In this set of parameters, we increase the average degree by 5 and the number of vertices by 10 K. And we visualize the evolution of the degree distribution of the generated graphs. And the second set of input parameters, we define the evolution of the graph with a peak in the mean or the average degree of the nodes. This indeed can represent the case of transportation networks, where the average connections or the average number of connections is subject to a mean during peak, to an increase during peak hours. And we also visualize the evolution of the degree distribution of our generated graphs. We also evaluated RTGen with another type of degree distribution, the Zipfian distribution. This represents power law distribution. Indeed, a huge or a large number of graphs have has a power law degree distribution that translates the fact that a small portion of vertices have a large number of connections, whereas the rest vertices have a relatively small number of connections. On this input, in this set of input parameters, we increase the maximum number of edges by 10, and we increase the number of vertices by 10K. Finally, to evaluate the community-aware feature of RTGen, we applied a community detection algorithm and visualized the obtained graph. Now it's clear that indeed the generated graphs embed a hierarchical community structure. Besides, by increasing the value of parameter k, we increase the difference between the within and between community edge densities. Now, the right side plot represents the value of the modularity and function of the parameter k. Now, the modularity represents the or is a metric that can measure the strength of the community structure of the graph. As we can see, the modularity increases with the increase of k. Hence, k is a tunable parameter, or is a parameter that can tune the strength of the community structure of the generated graph snapshots. To conclude, RTGen generates temporal graphs with any given evolution of the degree distribution and the community structure by extending the two well-known static graph generators, Changru and stochastic block models. RTGen can be used to assess the performance of graph-oriented data platforms by generating larger scale temporal graphs. Now, the community structure of the graphs generated by RTGen is static. However, the communities in real-world graphs are subject to splits, merges, growth, or shrinks. Hence, we plan to add this feature to RTGen. Thank you so much for your attention.
Yeah, thank you, Maria, and also thank you for being really on time. So I don't know if there are some questions from the audience. Okay, otherwise I have a couple of questions. So also given that we have time, we have seen from the keynote that there is a high dynamicity in the evolution of data in a data lake, and that also between data and metadata there are many relationships. So actually in the data lake we can have like a graph that represents the relationship of our data. So can you give us some application of this temporal graph evolution to improve data management with respect to application of this approach into that domain of data platform?
There is actually a number of applications for temporal graphs. For example, I'll provide the use case that I'm working on. Actually, we are working on a graph of IoT objects, and the temporal graph models the temporal or temporary connections between the different IoT devices. Now we are trying to design or develop a graph management system that can efficiently manage the temporal or the evolution of the temporal graph while minimizing the storage, of course, and optimizing the query variation of such graphs.
Okay. And then, okay, Patrick, please go on.
No, please go ahead, Matteo, if you have any more questions.
I had like a more specific question to this. And so in slide 7, you showed that we have an input to the approach is a parameter of the evolution of the degree distribution. And then also throughout the presentation, we've seen that we have many parameters. So I was wondering, how do you tune all of these parameters, and especially if you have evaluated this approach with respect to some ground truth. So for instance, if you have like a piece of social network such as Twitter, how do you like set all these parameters to resemble the behavior of a specific social network?
Do you mean how we can extract features from real-world graphs and try to simulate the same features using RTGen?
Yeah. So which feature do you extract, and how do you extract them? Yeah.
Now it's up to the user to characterize their application domain and the evolution of the graphs used in their systems. For example, they can apply a community detection algorithm on their graphs. They can extract the community structure and represent it as a stochastic community matrix that is an input for the RTGen. For example, if their graph embeds a hierarchical community structure, they can also characterize the parameters of the hierarchical tree. They can also track the evolution of the degree distribution, for example, the increase of the number of added nodes in each time step, or the increase of or the variation of the mean or the average degree. And they can, after this step, they can create a number of parameters or characteristics that can serve as an input for RTGen.
Okay, so Patrick, we have time for another question.
Yeah, thank you, Matteo. Thank you, Maria, for the presentation. I'm pretty sure that my questions are going to be very stupid, so I apologize in advance. My first question was about the evaluation of the generated graphs. Is there a way to actually compare what is generated with actual social networks? Would that make sense, by the way, and how to do it?
With actual social networks?
Yep.
Thank you for your question. Yes, of course, one can extract for example, as I mentioned before, the community structure of the graph. Let's say instead of the community matrix, we can use a metric that measures the strength of the community, that is the modularity. They can extract modularity or the evolution of the modularity, and then they can test or evaluate if this obtained or the modularity obtained by RTGen is near or as identical to the modularity of the social graph.
You mean that you would be somehow using I would say classical measures of distances between graphs? Am I right, or?
Actually, we have defined, but I didn't present it here. We defined several metrics or error or distance metrics between the desired parameters and the produced parameters. Those distances measure the difference, let's say, between the degree distribution of the generated graphs and the input parameters, and also the community structure.
Okay, thank you.
So maybe so this is Zoltan, so I'm a co-author, and maybe I just to add one point to this discussion. So maybe we should separate these two phases. So one is that to extract some features from real data, and the second is that to generate new data. So via this paper, we were working on this second thing, so on the second aspect. So we did not work on extracting features from existing social network, but to generate data. And what is the application of this generated data? For example, benchmarking data platforms. So in fact, this is what we use for. So we benchmark the data platforms of the company where Maria is working, and this is often very difficult because, as Maria explained, there are a lot of benchmarks for static data, but not so much for dynamic data. So this is why we did this work. So one clear application is the benchmarking of data platforms.
Yeah, understood very well. My question was more related to how realistic, from a like social network point of view, the generated data are. And I was wondering if there are some I don't know, commonly agreed measures that could be used to do so. But again, my question is a bit naive, so sorry.
So it's very difficult to answer how realistic is this, in fact, because well, it depends how do you want to characterize your realistic graph. So in fact, so it depends if what do you consider as realistic. So if you say what measures are characterize the realistic graphs, then we can compare. And then there, according to some measures that we have used, we have a very realistic graph. So, but if you choose completely different measures, then it might not be the case. But
I know realistic from existing. Oh, sorry, Matteo.
It's just because we run out of time. So if you want to proceed the discussion in the. So sorry to bother you, actually. An interesting talk, but we are running out of time. So thank you again for the talk, and I hope this will be some meat for discussion in the common room. And so in case we will discuss also that there. So we will need to move to the second paper. Second paper is towards a holistic data preparation tool. And the presenter will be Valerie Restat, but we will play the recorded version of the paper, and the question answer will be live, if I'm not wrong, Enrico.
Sorry, I was muted, couldn't find that. Yeah, you're right. Unfortunately, Valerie is not feeling too well, but okay, she's here to answer the questions. Sharing the screen with the recording.
Yeah, we see the YouTube.
Okay, here it goes.
Yeah.
Hello and welcome to the presentation about our paper Towards a Holistic Data Preparation Tool by Michael Kletzke, Uta Störl, and me, Valerie Restat. I will first present the current challenges of data preprocessing, then I'll give a brief overview of the state of the art of data preprocessing tools, and then I'd like to present the holistic data preparation tool we envision. The challenges of data preprocessing can be divided in two parts. One of them are the workflow properties regarding the preprocessing process itself, and the other one is data quality regarding the results of this process. At first, we look at data quality. There is no single definition of what data quality means, but it is undisputed that it includes many different aspects and does not only concern accuracy. In an analysis of definitions from 1985 to 2009, several so-called data quality dimensions were identified with timeliness, currency, accuracy, and completeness, to name the most referenced. In another paper, a hierarchical data quality framework was built with the dimensions availability, which includes, among others, the aforementioned timeliness, usability, reliability, which includes, among others, the aforementioned accuracy, which of course is not the only aspect, but still a very important aspect. And there are different metrics, for example, precision and recall, and also integrity constraints or functional dependencies are important. The next dimension is relevance, with, for example, fairness, a very important aspect, which I will go into more detail next on, and presentation quality. Like I said, fairness is a very important aspect of data quality. The problem is the data often reflects some kind of biases or historical perceptions, and this problem is even amplified when output of biased algorithms is in turn used for further predictions. And in addition to a bias already present in the data, a bias can also be introduced into the data through preprocessing. An example for this would be a form that offers a binary gender choice, so you can specify if you're male or female. And if we now assume that about half of the attendees were male and half were female and some persons were non-binary, and if we also assume that women were more likely than men not to specify their gender, and of course the non-binary persons would also not specify their gender, then we would have some missing values. And if we now choose a mode imputation, where we impute the missing values with the most frequent value, which would be male, then we would skew the distribution and even exclude non-binary persons. These two different aspects of data quality. And next, we look at the workflow properties. In a survey with data analysis and infrastructure engineers, it was shown that data cleaning is time-consuming and needs human involvement, and that it is an iterative process with an ad hoc evaluation. So the analysts try different algorithms with different parameters, then look at the data. Does it seem right? Does it seem wrong? Then maybe adapt the algorithms. So this results in this iterative process. In an analysis of data cleaning tools, it was shown that there is no single dominant tool which includes all the different error types that exist. There have been some improvements with the holistic multi-tool strategy and with domain-specific tools, but overall it was stated that human involvement is necessary and that there is a lack of intelligent solutions. This was also stated in another survey of data cleaning tools, that human involvement is necessary, both IT and domain knowledge, and that there is a lack of intelligent solutions, and also that most tools already require like a pre-processed version of the data set, for example, with specific headers or specific delimiters. With regard to big data, there are two main challenges. The first one is volume. Because of the ever-increasing amount of data, the data quality gets compromised, and many data cleaning tools do not scale sufficiently. And the other one is variety, because of the diverse data formats and the different error types that exist. Another important aspect is reproducibility, and the iterative nature of data preprocessing brings further challenges for reproducibility, and the data alone is not sufficient. So it's not sufficient only to have the raw data and already preprocessed data, but there's a need to understand the data lineage. And reproducibility of data preprocessing in particular has so far received little attention compared to other areas. Next, we'll have a brief look at the state of the art of data preprocessing tools. There are different tools and systems, but none of these systems can be considered a holistic tool, either because they only focus on a certain aspect of data cleaning, like error detection, or only on certain types of errors, like integrity constraints. Then IT knowledge is partly necessary in addition to domain knowledge, and the evaluation was mostly done on only one or few aspects of data quality, mainly accuracy. For example, fairness was mostly not considered. And most tools were only suitable for tabular data, so semi-structured and unstructured data was also not considered. In line with the aforementioned challenges, we now propose a holistic data preparation tool and would like to highlight some tasks that we think need to be addressed in future work. We look at them step by step, beginning with ensuring fairness. For a bias already present in the data, a tool like this should have support for extensive testing for different fairness metrics, and for a bias arising during preprocessing, the data changes and data distributions need to be measured. The consumer labels are conceivable here. If we think at the example with the mode imputation, there could be like a warning. With this strategy, we maybe skew the distribution. Of course, fairness is not the only aspect of data quality, so we think a tool like this should have a comprehensive integrated evaluation regarding all the different aspects of data quality, for example, through automated checks regarding to the arrival time, or to intervals of the data, or to the range of the data, or accepted values, then with different metrics, like I said, precision, recall, integrity constraints, functional dependencies, and with standards and specifications, and also consumer labels are conceivable. And next we look at the workflow properties. Like I said, human involvement is still necessary. Many tools are used by domain experts without in-depth IT knowledge. So we think there should be an abstraction from IT knowledge. Different approaches are conceivable, for example, visual and interactive approaches, or approaches based on natural language processing, for example-oriented approaches comparable to query by example. Still, human involvement is time-consuming, so it should be minimized, for example, with the usage of machine learning techniques that automatically configure the data preprocessing pipeline, comparable to automatic DBMS tuning, or with the usage of dictionaries or knowledge stores. Another important aspect is reproducibility. Like I said, the data alone is not sufficient, but there is a need to document the whole preprocessing process and provide a description which algorithms were used, which parameters were applied. And this will be one of our next research questions. We want to focus on how this can be achieved in the best way. With regard to big data, there were two main challenges. The first one was volume. Because of the increasing amount of data, tools need to be scalable. And the other one is variety. Like I said, most tools are only suitable for relational data, or tabular data. So the quality of semi-structured and unstructured data needs to be better explored. And this will also be one of our next research questions we want to analyze. Like I said, we envision all these different aspects to be combined in a holistic data preparation tool. And as a basis for this, we implemented Gouda for the generation of universal data sets. We have encountered the problem that data sets are either not publicly available, or that ground truth is missing, or that they include only a few different error types at low error rates, which complicates a comprehensive analysis. And therefore, we implemented a test data generator called Gouda. With Gouda, we can generate data with diverse error types at arbitrary error rates. We provide a ground truth, and we made this publicly available so that it can be used for testing and extensive analysis. So in this presentation, we presented the holistic data preparation tool we envision and main requirements and possible solutions for the two categories, data quality and workflow properties. We presented Gouda, the test data generator we will use for our next analysis regarding the topics of the data quality of semi-structured and unstructured data, and data lineage and reproducibility. That's it. Thank you for your attention.
Okay, so thank you for the talk. Also, Valerie is here. I don't know if there are some questions from the audience. Otherwise, I have one. And so in the slide on the where you were discussing the workflow property, you mentioned big data and two dimensions of big data, so volume and variety. Of course, there is usually the third missing one, that is velocity. And because in our data platform, usually we need also to integrate streaming and batch static data. So here you discuss the preparation of, let's say, more static data, but how do you envision also the integration of the preparation and integration of streaming and batch data? So do you have any idea on that?
Yes, of course, this is a very important aspect as well. Like the different data formats, like semi-structured and unstructured data, streaming data is of course very important, and we also want to analyze the difference between static data and streaming data, and analyze how we can adapt the algorithms already there for static data, and how can they be used for streaming data.
Okay, I don't know if there are other questions. If no, I thank you, Valerie, for the presentation and hope you are getting well.
Thank you very well.
Okay. So the next paper is towards human-centric AutoML via logic and argumentation, and the presenter will be Joseph Giovanelli. So hi, Joseph.
Hi, everyone.
If you are ready, the floor is yours.
Yeah, do you see my screen?
Yeah, you can see it.
Okay. Hi, everyone. I'm Joseph Giovanelli, and I'm here today to present the paper towards human-centric AutoML via logic and argumentation, which I wrote with Giuseppe Pisano. So let's start. In relation to data platforms, there are a variety of challenges to tackle. They range from the collection of the data, in which we can use either a data warehouse or a data lake, to the actual analysis of such data with the aid, for example, of machine learning. As a matter of fact, machine learning has been previously employed to cope with each and every type of real case problems. And it will be also the topic of this presentation. So finding a solution in machine learning tasks encompasses the instantiation of a machine learning pipeline that is a series of data preprocessing transformations that shape the data so that a machine learning algorithm can extract as many insights as possible. And this isn't an easy task. Indeed, to instantiate a step of the pipeline, we have to consider a wide range of techniques. And for each of the techniques, we have a set of hyperparameters to set, which have their own hyperparameters, which have their own search space. Besides, we have constraints. For example, the order of these transformations can affect both the performance and the validity of the results. To cope with such an issue, the data scientist usually leverages a standard process model as CRISP-DM that helps her to gather all the constraints and find a solution that is compliant to such constraints. CRISP-DM encompasses different stages. The first one is domain understanding, in which data scientist works in a close cooperation with the domain experts to list domain-related constraints that are intrinsic of the problem. Follows data understanding, in which we discover data-related constraints due by, for example, the data format. Then she tries different solutions throughout the next stages. In data preprocessing, she tries different data preprocessing transformations and discover transformation-related constraints. In modeling, different machine learning algorithms are tried with constraints as well. And then evaluation provides a way to measure the performance. Finally, deployment is devoted to the implementation of such a solution. Furthermore, we have cross-cutting constraints that regards ethical or legal sphere. For example, we have racism or gender equality that have to be treated, otherwise they could lead to social repercussions. So AutoML aims at automating the machine learning pipeline instantiation and to consider a wide range of machine learning algorithms as well as data preprocessing transformations. They find suboptimal solutions even in huge search spaces. Yet they require you to provide the search space and to consider all the constraints together. But this is not easy, considering huge amounts of constraints is overwhelming. Besides, to boost the performance, they leverage Bayesian optimization, meta-learning, assembling, lots of experiments that leads AutoML tools to be another black box to be understood. And for such reasons, AutoML doesn't allow the proper knowledge augmentation, is not compliant with the philosophy of CRISP-DM, in which iteration after iteration, the knowledge is augmented by acquiring more and more constraints about the problem. So we designed Amnet, a human-centric AutoML tool that helps the data scientist to redeem her centrality, because we think that she has the duty to revise the AutoML solutions and to supervise the whole process. We leverage logic to give a structure to the knowledge, to encode the machine learning constraints, and argumentation to deal with possible inconsistencies among these constraints, and also to provide human readable medium that is able to let the data scientist to revise the results. So specifically, data scientist leverages a logical formalism to enlist, to encode the constraints into the logical knowledge base. But at the end of the day, constraints are just rules. That kind of rules that can be extracted from machine learning experiments. And that's what AutoML does. AutoML performs several machine learning experiments. So we designed the AMLET architecture so that constraints and rules can be extracted from the result of the AutoML tool and update the logical knowledge base. In such a way, the logical knowledge base, the shared repository, that iteration after iteration is always up to date. And throughout the argumentation tools, and from the logical knowledge base, we create a problem graph that consider all the machine learning constraints together, discard the machine learning pipelines that are not compliant to such constraints, and created the AutoML search space. So AutoML can generate valid solutions, and also the problem graph is just a graph that can be discussed and interpreted by the domain experts and the data scientists. Let's see an example. So we have two different data processing transformations that are discretization, normalization, and a machine learning algorithm, namely decision tree. And here below, we listed all the 5 possible machine learning pipelines. By considering an algorithm-related constraints that requires discretization when applying decision tree, we have to discard the first and the third machine learning pipelines because they contain a decision tree, but not a discretization. Then considering another constraint, a transformation related constraint that says non-normalization in pipelines with discretization, then this leads us to discard the 4th and the 5th machine learning pipelines because they do contain discretization, decision tree and discretization, but they contain also normalization. So in the end, the only pipeline that is valid is the second one. In AMLET, we can encode all these informations in a logical knowledge base with intuitive logical formalism. In the first part, we can see the transformations as well as the algorithm. So the building blocks that will be arranged into our machine learning pipelines. And in the second part, you can see an algorithm related, the transformation related constraints. We highlight how intuitive this logical formalism is. And we developed this demo project in which we wrote a theory that is able to generate a problem graph with the aid of augmentation. In an augmentation graph, we have the nodes that are the definitions of the definitions we did in our logical knowledge base. And then we have also the pipelines that are that we have to consider. In the argumentation graph, the nodes are called arguments. Some of them are undefeasible, like T1, T2, and the A1, because they are the building blocks of our logical knowledge base. They cannot be defeated. Other ones, like the pipelines, are actually defeated. And we can see that the first constraint, namely the algorithm-related one, is attacking the first and the third according to what we saw before, because they do not contain the discretization. And accordingly, the second constraint is attacking the 4th and the 6th pipeline. So we can easily see and we can easily notice how AMLET highlights the valid solution. So all in all, we designed AMLET. It is a human-centric AutoML framework that helps the data scientists to redeem their centrality, to revise the AutoML to results throughout argumentation, and to supervise the whole process we leverage logic and argumentation to build the search space of AutoML as well as a human readable medium. So the road of FutureWorks is straightforward. We plan to find a sound formalization of AMLET and to develop a working implementation to finally test the efficacy and the benefits of our framework on real case problems. So thanks for attention.
Thank you, Joseph, for the talk. Are there any questions from the audience? Yeah, Stefano, please go on. Stefano? You are muted.
Ah, sorry, I had
Okay.
pressed the wrong button. Yeah. I was saying once the user has inputted to the system these constraints and rules, it may happen that there is a conflict between these rules. So there is no, in all cases, there will be no possible solution. Do you think that adding some sort of a check mechanism to find if some conflicts exist could be beneficial, or do you think that the probability of a conflict is actually very low, so it's not worth?
Well, argumentation is actually done for that. I mean, in the legal fields, argumentation is primarily applied because you have different laws and they are like in conflict with each other. And based on the semantic of the argumentation tool, you can decide which argument in contrast to the other wins or lose. So is for sure beneficial to deal with such inconsistencies, and we plan to do that.
Okay, thank you.
You're welcome. Thank you.
There is time for another question. I don't know if anyone has it or I do. So, okay, my turn. And so in slide 3, you mentioned that we have also domain-related constraints. And then you say that with a logical representation of this constraint, one can build like the constraint to manage all the problem graph. But what if after like running our AutoML pipeline, can we learn actually these constraints? So can we learn from the space that have been actually explored if there is a logical representation that can we learn, saying that, okay, these constraints that I didn't know actually exist. So can we do that?
Yeah, is actually what we plan to do, because CRISP-DM is an iterative process. So you acquire some constraints, you put them in AMLET, you generate the search space, AutoML runs, and actually discover some constraints that you didn't know to know. Some constraints you didn't know, and these constraints are going to be part of the logical knowledge base. So the logical knowledge base is going to be augmented by the AutoML tool run, and yeah, this is fundamental for our framework actually.
Yeah, and also it's fun to see that you provide an AutoML automation and then you bring back the human in the loop. So it's really nice. The idea is nice. Okay,
thank you.
So thank you, Joseph. Thank you also for your answers. And so next paper is ECDP, a big data platform for the smart monitoring of local energy communities. And I think we have Luca. That is.
Can you hear me?
Yeah, we can hear you fine. We can hear you and see you. So yeah.
Okay, can you see the screen?
Yeah, we can see the screen, so the floor is yours.
Okay. Good morning, everyone. I'm Luca Gagliardelli from the University of Modena, and today I present the Energy Community Data Platform. So the platform aims to collect and analyze data about the energy consumption and production of local energy communities, which are groups of users that produce and consume energy. And the main goal of the platform is to optimize the self-consumption of the produced energy. And the project is funded by the Italian Ministry of Economic Development and involves 3 main partners. ENEA, which is a public body that commissioned and supervised the project, the database group of the University of Modena that designed the platform, and DataRiver, which is an innovative small-medium company that implemented the platform. So the development of the platform was guided by 3 main projects that were already developed by ENEA. GECO, that aims to promote the self-consumption of energy produced by the local energy communities. Self-Users, which is a project that collects data from a smart building to measure the energy consumed and produced with the goal to optimize the self-consumption, again. And PEL, that is a project that collects information about public lighting systems, measuring and analyzing the energy consumption to optimize it. So ENEA already implemented an ingestion system to collect the data coming from these projects, and the raw data coming from sensors are stored in the so-called triage area in CSV and JSON format, while structured data are stored in a Postgres database. And structured data could be also raw data coming from the triage area that are already cleaned and processed by ENEA. So the platform they ask us to design requires to collect data from many heterogeneous data sources, requires to perform streaming and batch data analysis, and mainly manage time series, because actually the data coming from the sensors are associated with the time and also with a geographical position. And the platform continuously ingests data that after the ingestion don't have to be changed again. So they are actually time series. Then there is a need to perform temporal and spatial queries to store all the raw data for further analysis, and also to perform a data integration of the different data. Moreover, all these tasks are to be performed by using only open source solutions. So this is the resulting platform that we have designed, and let's see in detail the components that compose it and some use cases that guided us in its design. So MOMIS is the core of the platform and is a virtual data integration tool since the data are integrated at query time. But to speed up frequent queries, the integrated data can be stored inside a database. In this case, we use the Postgres. And as I said before, MOMIS is the core of the platform and is used to ingest, clean, and integrate the data. Moreover, it connects the storage layer with all the other tools, so with the rest of the world. And mainly we choose to use MOMIS because it was designed by our research group during the years, and now it is maintained by DataRiver. So we have a nice, an high expertise with this tool. And to store the integrated data, as I said before, we employed Postgres that was equipped with timescale and Postgres extensions that allow us to perform temporal and spatial queries, which are fundamental to perform the analysis on our data. And moreover, Postgres is used as a cache to store, as I said before, the integrated data. To store all the data, all the raw data, we employ the Delta Lake, which is a storage framework that offers many interesting features such as edged transactions, scalability, data versioning, metadata, possibility to store the metadata. And also it offers the possibility like a DBMS to have a log file that could be useful in case of data loss. And many more features that we cannot see it from this slide. In the platform, we use it to store all the raw data and also as a historical archive to store the integrated data that are periodically moved from Postgres to Delta Lake to keep the performance of Postgres at the maximum levels. And we choose to use Delta Lake mainly because it is fully compatible with Spark, which was already used by ENEA in their project. So we need to keep the compatibility with the system. Airflow is a scheduler and is used in the platform to automate several tasks such as the ingestion of the new data or moving data from Postgres to Delta Lake. And we used to choose Airflow mainly because it is fully customizable to Python scripts, and also it's able to manage and control Spark jobs that are used inside the platform. The Momis dashboard is a visualization tool, and it can be used to perform data analysis or data analytics tasks. And we employed it because it's strictly integrated with Momis, but the platform is not limited to it, and other data visualization and BI tools can be used through the provided APIs that was implemented. So let's see some workflows and some use cases. So here we can see the ingestion of the raw data. So the wrappers of Momis are used to load the data inside the Delta Lake. Then Momis is used to clean and integrate the data, storing the result in the Postgres DBMS. And the users can directly query the data from Postgres by using the Momis dashboard or by using the REST APIs. And periodically, as I said before, the integrated data are moved from Postgres to Delta Lake to have an historical archive mainly, and also to enhance the performance of Postgres. So limiting the quantity of data stored inside the database. And also, as we can see here in the point 4, the advanced users can directly perform data analytics tasks by using Spark on Delta Lake. So they have access to all the raw data and can perform data advanced tasks like machine learning pipelines or other tasks like that. Here we can see another workflow in which the data coming from a structured data source. In this case, the data was already cleaned and processed by Enea in this case. So they can be directly stored inside the Postgres database. And then the data will follow the process we saw in the previous slide. So finally, the data about the PEL projects are stored in a dedicated server. And in this project, MySQL is used to store structured information about the lighting systems, while the consumption data are stored on an Hadoop file system in a JSON format. And here Spark is used to combine the data to produce a data frame that is directly stored inside the Delta Lake. And then again, the data will follow the same process we saw before. So in conclusion, we presented the energy community data platform to store and analyze data about the local energy communities with the goal to optimize the self-consumption of the produced energy. And the main lesson we learned in this project is that keeping different workflows separated by using a modular architecture led to obtain a more general system that can combine the strengths of each tool and also maximize the scalability and the flexibility of the system. And this let us to meet the needs of the different users. So for instance, advanced users that need to access to the raw data, or basic users that just need to see integrated data at a higher level. So finally, we can state that the design platform could be reused in other time series management projects due to its flexibility and yeah, mainly for this. Okay, I have concluded. Thank you for your attention. If you have any questions, I'm happy to answer.
Thank you, Luca, for the talk and also for being on time. So is there any question from the audience? Stefano?
Yeah, I saw that, especially probably in the first of your use cases, you have a very massive amount of data that are being loaded to the system, right? Because your streams are very, very quick, let's say. So I wonder, what about the querying performances? Can you do you have real-time performances, right time, or is it a second, a minute, or what?
Okay, actually, to be honest, I don't know actually the true response time, because this part was led by DataRiver. I saw that one member of DataRiver is here, maybe he can answer the question, but I know that they had some problem with Delta Lake, because the Delta Lake is a storage system that is strictly related with the Spark. And so every time they need to query the data from Delta Lake, they need to launch, a Spark system. And so the performance are not so good when we have to query directly the data from Delta Lake. This is the reason, the main reason why we use the Postgres as a cache. So when the users need to, obtain the results, integrated results, in fast time, Postgres is used in this case. Delta Lake works well when we have to perform data analytics very easy. Data analytics tasks that are performed in batch way. And these are the things that they told me from DataRiver, but yeah, I don't know if they want to answer, if Luca can answer to this question. I saw that it was connected later, but
do you hear me?
Yeah. Okay.
We use both Delta Lake and Postgres DBMS based on the use of the data. If I have to have a query in a short time, I store the data on Postgres. So Postgres is focused on real-time data. If I have to do an historical analysis and I have to do the query with the offline data, Delta Lake works well. So for this reason, we define this solution an hybrid solution.
Okay.
But the Postgres is a relation database, so it responds in milliseconds. While the Delta Lake use an amount of seconds, 30. This is the average time.
Okay, thank you.
There is also a question from Enrico.
Yeah, just a follow-up question. So why are you using Postgres for this job and maybe not some distributed key value store, which can guarantee fast performances, but also scalability?
Okay. Luca, do you want to answer or I try to answer? Okay. I think Postgres was used mainly because we need to perform time query related to the time. So for instance, to perform aggregation based on time and to actually, yeah, the main, we choose to use Postgres with time scale.
Exactly.
Mainly because we have to perform query related to the time. So we have to perform aggregation queries, for instance, to change the scale of the data based on time, and time scale offers this opportunity. So this is actually the main reason why we choose this system. And
Okay.
time scale is an extension of Postgres. So we are, we need to use Postgres to use time scale.
Of course. Okay. Thanks.
Okay. So thank you, Luca, for the presentation and for the answer. And also, I think that this really answers the question Panos posed to Alberto during the keynote, meaning that you have plenty of stuff to do, and so also the technological stuff you need to answer all these requirements is it's actually really heterogeneous and probably it's not so easy to manage. Okay, so let's move to the next paper. So the next and last paper is Darwin, a data platform for scheme evolution management and data integration. And I think the presenter will be Jutta. Yeah. Okay, so we
yes,
can.
That's right.
Yeah, we can hear you and see your screen, so the floor is yours.
Okay, thank you very much. I would like to present Darwin, a data platform for NoSQL schema evolution management and data migration. The motivation from Darwin came from agile software development. Agile software development implies frequent schema changes, weekly up to daily, depending on the application scenario. And so schema flexible or schema-less NoSQL databases became very popular within agile software development. However, it's still an open question how to manage the variational data, which means if you have a database already in production and you manage different application versions, then data will be in different structures, different versions in the productive database. And state of the art today are migration script within the application code or something like this, which of course is expensive and error prone. And so schema evolution, especially in context of NoSQL databases, is still one of the most challenging questions nowadays. And so we proposed an optional schema management for NoSQL databases. Of course, you have scenarios where you do not need this kind of schema management and use the flexibility of NoSQL databases or the schema-less of NoSQL databases, but there are a lot of application scenarios where we think it's necessary to have a schema management on top or inside a NoSQL database. And for this challenge, we designed and developed Darwin. Darwin is a middleware, a schema management middleware between the application and the different kind of NoSQL database systems. Darwin supports the whole schema management lifecycle. We are able to declare a schema or to extract the schema as well as schema version history. I will come back to this point in the next slides. And after managing the schema evolution, we are able to migrate the data with help of different data migration strategies proposed by Darwin. Darwin is implemented for different types of NoSQL database systems, for instance, for document stores like MongoDB and Couchbase, white column stores like Cassandra, or multi-model database like ArangoDB. And the architecture of Darwin is very flexible, very extensible to support other kinds of NoSQL database systems. The first data preparation task is schema extractions. As I already mentioned, there may be variational data in the productive database, and you may have already started with your application development and now start to try to manage the schema and the data in a good process. And so you have to extract the schema as well as the schema version history. There are a lot of approaches which extract its static schema, but to best of our knowledge, Darwin is the only tool supporting the extraction of the schema version history. So it's very important to manage the schema. And after managing the schema, we can start the data migration as a safe process based on this schema evolution management. There are different kinds of data migration strategies. For instance, eager migration, where all data is migrated after the introduction of a new schema. The advantage of eager migration is that all data is homogeneous after the migration. But the disadvantage is the migration cost. Migration cost in terms of time during the migration, but also migration costs in terms of money when the database is hosted in the cloud. So another kind of data migration is, or another strategy is lazy migration. Using lazy migration, there's no data migrated after introduction of a new schema version. Data is migrated on the fly when the data is accessed. So of course, you have a very low migration cost because only the data needed is migrated. However, there may be a significant overhead on runtime in terms of latency, data access latency. So the question is, are there any compromise, any kind of data migration strategy between eager migration and lazy migration with a compromise of latency and migration costs? We introduced some kinds of proactive migration strategies. The most interesting one is predictive migration. In Darwin, we manage a prediction set. And with help of this prediction set, we try to keep the hot data up to date. So we can vary the size of this migration of this prediction set. And so we are able to reach a compromise between migration costs and latency. And the possibility to change the size of the prediction set gives us also the possibility to implement a kind of self-adaptive data migration. So depending on maybe SLAs regarding the latency or the migration costs, we are able to adapt the size of the prediction set and so adapt the amount of data which is proactively migrated. But the general question is, what is the appropriate data migration strategy? This decision, of course, depends from the characteristics of the data set, from the data access pattern, from the characteristics of the schema evolution, which means how often schema evolution occurs and which kind of schema evolution operations occur. And of course, from different other parameters like the DBMS use, the distribution, the replication factor, and so on. And last but not least, from the cloud pricing model in case when the database is hosted in the cloud. And to answer this question, we designed and implemented on top of Darwin MICCAST. MICCAST is a data migration advisor. In that MICCAST, there is a workload simulator, a cost calculator, and a latency profiler. And as input from MICCAST, we can specify the characteristics of the data set, the data access pattern, the data model changes, which means schema evolution characteristics, and the DBMS and the cloud price. And with help of Darwin, MICCAST uses Darwin via a REST API, we simulate the workload, calculate the cost, and determine the latency. And then you get an output on migration costs, estimated migration costs, and data access latency. And to support the reproducibility of the experiment, the configuration of the performed measurement, as well as the result, are stored in a separate MICCAST DB. MICCAST looks like this. You can specify, of course, you have also a CLI, but you can also specify on a web interface the data and the data characteristics, the schema evolution characteristics, and the cloud pricing model. And after the simulation and calculation run, you get an output. You can see that depending on the used data migration strategies, there are significant difference in terms of migration costs as well as in terms of latency. So to conclude, I presented Darwin, a schema evolution management middleware to you. Darwin enables continuous agile software development with NoSQL databases. And as an important contribution, Darwin helps to understand and estimate the impact of different data migration strategies, and so helps to choose the appropriate data migration strategy. We make Darwin publicly available within a GitHub repository, and you may also have a look into usage of Darwin via a demo video which we published on YouTube. In the future work, we want to extend Darwin to use environment, so we will be able to migrate, not only migrate data between different polystores, but also between different kinds of NoSQL databases, but also to optimize the schema, because we all know that NoSQL databases have different characteristics depending from the data model. And we also want to extend the ability of Darwin in terms of self-adaptive data migration, which means to choose the appropriate data migration strategy or to adapt the parameters of the data migration strategies. So thank you for your attention, and I'm looking forward to your questions.
Okay, thank you for the presentation and also for being on time. Is there any question from the audience? Otherwise, okay, so Stefano.
Yeah, well, thank you for your talk. One thing you said in the beginning, if I got it well, that you are automatically extracting the version history, right? Mm-hmm. So how do you map the concepts, the attributes, let's say, that you have in different versions? Is this done based on, because you're keeping track of the versioning operation that has been made, or are you doing this afterwards using some techniques for putting together matching attributes somehow?
Yeah, yes. This is a use case where we do not have any knowledge about the history. We do not know the schema evolution operations, and so we extract the data. It's necessary to have some kind of timestamp, to have a history of the data. And then we build schema graphs, and along the timeline, we match the different schema graphs. And of course, there are some schema evolution operations which are easy to extract, like adding or deleting an attribute. And there are some challenging operations. If maybe the difference between a rename or an add and delete, or moving an attribute from one entity kind to another entity kind may not be able to automatically resolve these ambiguities. So we also experimented with some algorithms based on analyzing the data. So that's a really challenging task. And after extracting this, we have the different schema version and also derived the schema evolution operations.
Okay, thanks.
Is there any other question? Otherwise, I have one. And so you mentioned that now we have schemas with different versions, and then you have the migration strategy. So how do you automatically migrate data from schemas that could be like incompatible? So if, for instance, you are adding new attributes, probably is fine. But if you move an attribute from one schema or the other, or if you delete an attribute, I don't know. So how do you deal with it automatically?
We first extract this kind of schema evolution operations, and then maybe if you access one piece of data, then we store these schema evolution operations, and then we have to migrate this step by step. We have also proposed some kind of optimization, for instance, to summarize some operations to optimize this process. But there may be cases where we have to migrate a lot of data, because maybe there are some data which is moved from another entity type, and there also maybe in the history was another operation from another entity type. So accessing one piece of data can initiate like a cascading data migration. So it's it's really not an easy task, and you have to be aware of this. So it's also, we called it single type operations and multi-type operations. Single type operations are on one entity kind, it's like add and delete and rename. That's easy and cheap cost. But if you have operations like copy or move between different entity types, it may be very expensive.
Yeah, so in the end, probably you will need something like a cost model. Oh,
yes.
Okay. Okay. So I think that there is time for a really quick question. Otherwise, I'll leave the floor to, I don't know, Stefano and Enrico for the farewell. So is there any other quick comment on this? Okay, so I leave the floor to Enrico.
Okay, so from my side, I just want to thank all the presenters and clearly everyone who participated in these sessions. I have to say that we had a very good attendance rate as compared to the other workshops. It was always between 20 and 30 persons, so that's really very good. So thanks again, and maybe meet you next year, who knows, for a second edition. Enrico, Patrick, I don't know if you want to say something.
No, I think, well, it's been nice having this workshop. Presentation have been very interesting, and yeah, Stefano said, maybe we'll see if we're going to be able to do a second edition. Let's see. But otherwise, we can close this up. Maybe we can see each other during the conference on the other workshops. Well, that's it.
Okay. Yes, nothing more to add except that it was very nice to have these discussions around this, the works presented this morning. Thank you to all.
Okay, so
let's meet in person next time.
Yeah, hopefully.
Bye.
Hopefully.
Goodbye.
Okay, thanks everyone.
Bye.
Bye.
Bye, thank you.
Thank you.
Thank you. Bye.